Today we will be discussing about Juncker's gas calorimeter, that is the Juncker's gas calorimetry, and which is used to determine the calorific value of the gaseous fuel. The simplest known calorimeter, that is an apparatus which is used to measure the quantity of heat in calories, is the coffee cup calorimeter as depicted in the diagram. Now, the coffee cup, which is made up of the styrofoam cup and it consists of the hot liquid that is placed, the inserted thermometer actually measures the rise in temperature of the substance which is heated or the fall in temperature when it is actually cooled up. And by this simple apparatus, we can measure actually what quantity of heat is liberated by this hot or the cold liquid when it is placed in the styrofoam cup with measuring the rise in temperature. The basic simple principle is applied for measurement of the calorific values of the gaseous, solid, liquid, fuels, etc. Now, the calorific value. As we know that the fuels can be solid, liquid, or the gaseous fuel. And the quality of the fuel depends on this particular value, that is the calorific value. It is defined as the total quantity of heat which is liberated by burning a unit mass or volume of the fuel completely. Completely means a complete combustion. If we have the solid or liquid fuel, then the calorific value is given by Q by M, that is the quantity of heat liberated per unit mass. And if we have a gaseous fuel, then it is given by Q by V for the gaseous fuel, that is per unit volume. So in this manner, the calorific value per unit amount of the substance, either mass or volume, is actually used for calculating the calorific value. When we are measuring the quantity of the heat, then it is measured in different forms. That is the simplest unit, calorie. It is the amount of heat which is required to raise the temperature of 1 gram of water by 1 degree centigrade, that is 15 to 16 degree centigrade. We also have the relation between its various units. 1 calorie, it is equal to 4.185 joules, equal to 4.185 into 10 raised to power 7 ounce. A bigger unit, kilocalorie, it is amount of heat required to raise the temperature of 1 kg of water by 1 degree centigrade, 15 to 16 degree centigrade. The relationship between kilocalorie and calorie can be written as 1 kilocalorie is equal to 1000 calories. There is another unit called as the British Thermal Unit, BTU. It is the amount of heat required to raise the temperature of 1 pound, that is 1 lb or libra water by 1 degree Fahrenheit, that is 60 to 61 degree F. The relationship stands for 1 BTU is equal to 252 calories. It is equal to 0.252 kilocalories. It is equal to 1054.6 joules. And also 1 kilocalorie is equal to 3.968 BTU. There is another unit called centigrade heat unit or the CHU. It is the amount of heat required to raise the temperature of 1 pound, that is 1 lb or libra water by 1 degree centigrade, that is 15 to 16 degree centigrade, and 1 kilocalorie is equal to 3.968 BTU. It is equal to 2.2 CHU. Interrelation between the different units of the CV discussed earlier can be summarized as for solids and liquids, since the calorific value is expressed as per unit mass, is given as 1 calorie per gram, 1 kilocalorie per kg, or 1.28 BTU per lb or a libra, that is actually the pound. Then for gases, since it is per unit volume, 1 kilocalorie per meter cube is equal to 0.1077 BTU per cubic feet, and also 1 BTU per cubic feet is equal to 9.3 kilocalories per meter cube. Types of calorific value. There are different types of calorific value. The one is actually called as the higher calorific value and the another is called as the lower calorific value. Higher calorific value is the amount of heat which is produced when a unit quantity of fuel is burned completely and the product of combustion are cooled to a room temperature. Mostly all types of fuel contain some hydrogen, and this hydrogen present during the combustion combines with oxygen and is converted into the steam. As the products of the combustion are cooled down to room temperature, the steam gets condensed into water and the latent heat of condensation steam also gets included in the measured heat. The calorific value thus measured is called as the higher or the gross calorific value. In a simple diagram, it can be represented as if you have the combustion process carried out in a closed container with the substance burned in presence of oxygen and the mass of the substance is m, then it will produce the product of the combustion. The heat will be given out, and at the same time, water vapor, steam, and other gases product will be formed. It will happen that the gas and the water vapors will condense, and then comes into picture the latent heat of condensation or steam. So total heat given out is Q1 plus Q2 divided by M, and it is an higher value called as the HCV. LCV or the net calorific value, the lower value as compared to the higher calorific value, it is the total amount of the heat produced when a unit quantity of fuel is burned completely and the product of combustion are not allowed to cool down to room temperature. That is, they are allowed to escape out. Since the products are permitted to escape out, that is, the water vapors and moisture, etc., are not condensed and escape out with hot combustion gases. Hence, the latent heat of condensation of steam is not added, resulting in the lower calorific value and is called as the lower calorific value or the net calorific value. It can be seen in the diagram that we have an open container, the combustion process is carried out, and the gases and the water vapor escape out. So there is no latent heat of condensation of the steam added to the quantity of the heat liberated. So the calorific value is simply the quantity of heat liberated, that is Q divided by M. So relationship between the HCV and LCV. The higher calorific value is greater than LCV, and also LCV is equal to HCV minus 0.09 into H into 557 calories per gram. Now LCV refers to lower calorific value, HCV refers to the higher calorific value. H here represents the percentage of hydrogen in the fuel. The unit 557 is actually the latent heat of condensation of the steam. If it is measured in calorie per gram, the LCV and HCV will be in the same corresponding unit. Let us derive the relationship as we have observed. Let the percentage of hydrogen in the fuel is H. This hydrogen actually combines with oxygen to produce the water according to the equation H2 plus half O2 gives H2O. On weight basis, it can be seen that the 2 grams of hydrogen combines with oxygen to form 18 grams of water. If we consider 1 gram of hydrogen only, then it will produce 9 grams of water. So this is the relation that if in the fuel 1 gram of hydrogen is present, the water produced will be 9 gram. Now, since 100-gram fuel is taken, then 100 gram of the fuel will contain H grams of hydrogen and 1 gram of fuel will contain H upon 100 gram of hydrogen. Since 1 gram of hydrogen is producing 9 gram of water, so H upon 100 gram of hydrogen will have the relation as 1 gram of fuel will produce 9 into H upon 100 grams of water. The latent heat of condensation of steam is 587 calories per gram. So, this much quantity of water when produced will produce the latent heat of water formed will be equal to 0.09 into H into 587 calorie per gram. Using this relationship, the LCV is equal to HCV minus 0.09 into H into 587. The LCV of the gaseous fuel can be calculated by the apparatus Junker's calorimeter that we are discussing here. It is based on the simple principle that a known volume of the gas is burnt at a known pressure and at a uniform rate. The heat that is liberated by this burning gas is absorbed by water. The water at constant rate is allowed to flow and it absorbs the heat liberated by the burning gaseous fuel. Now, by knowing the initial and final temperature of the water, quantity of the water, and weight of the water condensed, determination of the calorific value is actually carried out. If we look at the description of the Junkers calorimeter, it consists of the following part. First, the Bunsen burner. It is a gas burner and can be easily clamped and also moved in and out of a chamber called as the combustion chamber. Then gas meter, it measures the volume of the gas burned per unit time. Then pressure regulator. It controls the supply of the gas at a given pressure. It is provided with a drum floating above the water. It can be seen in the diagram that this is actually the gasometer. Now this is actually the gasometer, the glass for regulators, and then the Bunsen burner which is inserted in this combustion chamber. And another diagram depicting the same assembly, you can see that this is the needle which actually measures what volume of the gas is passed through this in a unit time. It passes through this gas holder, floating drum over water, that is the gas regulator, and then the gas actually is connected to the Bunsen burner where it burns inside the combustion chamber. This is the assembly in the laboratory representing the same, and the inlet and outlet for the water, and the water is finally collected out. Now, in a simple diagram, it can be seen that first of all, the gas is actually entered into a gas meter, which actually measures the volume of the gas that is passing through it in a unit time. The gas then passes through the pressure regulator, which actually maintains the pressure of the gas by the help of a floating drum over water and is connected to a manometer. The gas then reaches the Bunsen burner, where the combustion process of the fuel takes place, and in a chamber which is actually called as the combustion chamber. Now, due to the combustion, the gases product and the hot gases are actually produced. These move in these empty spaces and heats up the water which is present in the coil surrounding this gases chamber. Now, the cold water is made to flow through this reservoir, and then the temperature of this inlet water is noted with the help of the thermometer. The water circulates around the hot gases and finally gets collected into a hot mixing bath, where again the temperature is noted, outlet temperature is noted with the help of the thermometer, and the measuring vessel is used to calculate what quantity of water is actually received or is actually heated up. Now the exhaust gases actually pass out to the atmosphere, and again the temperature can be noted of these gases that are coming out, and the condensate water droplets are measured, then the quantity of the steam condensed is calculated, and this is actually utilized for measuring. This is actually utilized for measuring the LCV value. Now for the HCV and the LCV values. So another diagram representing the same thing, that is actually the gasometer, the pressure regulator, the Bunsen burner, and the uh, combustion chamber. The main heart of this calorimeter is actually the gas calorimeter, and which is actually consists of a vertical cylinder known as the combustion chamber, surrounded by annular water heating space and heat exchanging coils. As we have discussed, the whole apparatus is covered with a outer jacket, heavily chromium plated, to reduce the heat loss by radiation. The outer jacket works as a heat insulator. The annular water heating space is connected at its lower end to an internal water supply. Upper end of this space leads the flowing water into a hot heated water mixing bath. Now from the heating mixing bath, the water goes out into the sink through an overflow. The temperature of the water is measured in inlet and outlet point. The product of combustion gives the heat to the water flowing up in the heat exchanger coils. The outlet at the base removes the waste gases. Now, also, the gas which is burnt is enriched with water vapors, therefore, the water formed by condensation steam is also collected. We have the following observations. Let V meter cube is the volume of the gaseous fuel which is burnt at a given temperature and pressure in a certain time. It is converted to normal temperature pressure volume. Then the capital W kg, that is the weight of the water which comes out after absorbing heat. Small w kg, weight of the condensed steam. Let T1 degree centigrade is the temperature of the water inlet, and T2 degree centigrade is the temperature of the water outlet. Based on these observations, calculations can be actually carried out as: let high calorific value of the gas as fuel is C kilocalories per meter cube. The heat absorbed by the circulating water is given by W into T2 minus W into T2 minus T1, and the heat produced by combustion of the fuel can be given as V into C kilocalories per meter cube. Now, when we place the container having hot water in this, then we can see that the heat which is given by the burner is absorbed by is absorbed by the container and the water in it. So the simple formula, that is heat produced is equal to heat absorbed. So the heat produced is V into C, heat absorbed W into T2 minus T1. Now, based on this, HCV or C can be calculated as WT2 minus T1 divided by the volume V. So, in this way, if the lower calorific value of the gas as fuel is L kilocalories per meter cube, and the rate of water condensed for 1 meter cube of the fuel is given by small w per v kg meter cube, where small w is the weight of the water condensed during the process of this combustion, and the latent heat of the steam condensed per meter cube will be then given by w upon v into 557 kilocalories per meter cube. So LCV will be HCV minus latent heat of steam condensed per meter cube of the gas. So this relation is used as for calculating LCV, which is HCV minus latent heat of steam condensed per meter cube of the gas, and the formula used is LCV is equal to W T2 minus T1 oblique V kilocalories per meter cube minus W upon V into 557 kilocalorie per meter cube. So this is actually the calculation, the observation how the calorific value of the gas as fuel is calculated using a Junker's calorimeter. I hope this lecture was sufficient enough to explain the concept of using Junker's gas calorimeter for calculating the value of calorific value of a gaseous fuel.